0, and we get, well, it's to be 0 equals 2x squared minus 10x plus 1x minus 5. If I, what times what's negative 10, you add together, you get negative 9. If I do that, I'm just factoring it real quick. GCF, we get 2x, x minus 5. Take out a 1, and x minus 5. So we have 2x plus 1, x minus 5 gives me intercepts at negative 1/2 and 5. All right. Vertical asymptotes. I'll be at x squared minus 16 is 0, so it's going to be x is plus or minus 4. And yes, if you have quadratics in the denominator, you could have 2 asymptotes. If you have a 4th degree polynomial, you could have 4 asymptotes. If you had 5th degree, you could have 5, and so on and so forth. So that's what you're looking at. But you're just looking for your real zeros.
Like, how do you know where in between those they go? Like, you just start plugging.
Exactly. So now you've got, and then this one you had same degree top and bottom. So your horizontal was at 2.
Yeah.
So this is a really good example of how to guess. Let me do this. So if I start putting this one together, I know we didn't have to graph this one, but if you start looking at, it's a good example as far as where are you going to be looking at numbers. Horizontal at 2. Vertical is at plus and minus 4.
I wish I had a smartphone. That made graphics much easier.
It would, right?
Yeah.
So now,
Oh, is that plus or minus?
right. So now you've got 3 different sets of domain to search for. What you're going to want to do is you want to pick values within the domain here, here, in here, and in here. So you're going to choose a bunch of sets of numbers. When you get double vertical asymptotes, there's a little bit more plug and chug involved. Okay? So if I'm looking on the left-hand side, I'm going to pick maybe -5 and -7, just to get a good idea.
Did you just randomly pick those?
Yeah, I'm just picking 2 to the left of that one asymptote. I'm going to pick some in between. I'm going to pick maybe -2, -1, 0, 1, and 2. It is, but with all the quadratic stuff, you might get lucky that some are repetitive. Some of them might not be, you never know. And then on the other side, I'll probably pick out the 5 and the 7 on the other side. Now remember, you're using the calculator to do these things. Whether or not, I mean, if you have the dummy calculator, I guess it takes a little bit longer to type them through. But for last night, if I'm doing this last night, just to get, or even tonight as we're starting this, is it the end of the world if I go ahead and I put that in my table just to get an idea? Or should I just start practicing? Well, if I practice, I go -5, well, let's see, 2 times 25 plus 45 minus 5, I get 90. So this would be 90 over 25 minus 16 over 9, so it'll be at -5 and 10. There's my first ordered pair. I do the same thing with the -7. 2 times 49 plus 9 times 7 minus 5. 156 over 49 minus 16. So 156 divided by 33 is 4 point something.
Okay, yeah, this is what I did wrong. Because I was like, okay, and we had like the graph part, and then I got confused.
So I'm here-ish. So these are probably curved. No, you didn't have to graph this, but I'm showing you the basic idea of where it's going to look like.
Oh, okay.
All I'm doing here is picking numbers to the left. Hold on.
Wait, can't you just put it in like the table and
But I'm not going to let you use that calculator when we take a quiz on this. So I want you to stay away from using your table for right now.
can we use a dummy calculator? I don't know.
Everybody else but you, because I've said that like 6 times.
I was like,
It was. I feel good about that too. I go through, sorry, Chief. I go through again. I go 2 times 4, 8 plus 18 minus 5, I get 21. 4 minus 16 is 12, so 21 divided by negative 12. I get negative 1 point something. So at negative 2, I'm at negative 1 and change. At negative 1, so it would be 2 plus 9 minus 5 is 6. 1 minus 16 is 15, so 6 divided by 15 is negative 0.4. Here-ish. At 0, I get 5/16. Then at 1, 2 minus 9 minus 5 divided by negative 15 is 0.8. And then I go for 2, so it'd be 8 minus 18 minus 5 divided by negative 12, 1.25. And then at 5, 50 minus 45 minus 5, I get 0. Yay. And 7 was what? 49. 2 times 49 minus 63 minus 5 divided by 49 minus 16. I have 1. Almost 1. So it's probably doing this. In the middle, I'm not exactly sure what a toy looks like. It's probably somewhere along these lines. I don't know what's doing the tail there. I don't know if it drops or not, but that's kind of what you're doing. Yeah. And I have another example here in a minute that I'll show you when you get 3. Okay? Now, if you wanted to double check that, then throw in your calculator in your table, in your actual graph then. 2x squared minus 9x minus 5 over x squared minus 16. Oh, my window's all messed up. Yeah. And what happens here, if you look at change your window around, you'll see that the graph in the middle, it jumps the asymptote. That happens. You can have asymptote jumpers. That happens usually when you have the setup where you've got quadratics over quadratics. When you get this 3 setup, this 3 value, sometimes you can get that middle value to jump an asymptote, and that's perfectly normal. Okay? It's perfectly normal that it does that. A lot of times, we'll probably talk about this more tomorrow, is that there is a thing called jump discontinuity. I know it sounds weird. Basically, if you think of it this way, is you can have a vertical asymptote and a graph go through it, because what happens is, if you had, I don't know, if you had the polynomial, let's say it was x minus 3 and x plus 1 was in the numerator, and the denominator was x squared minus 1, so it was a difference of squares. This would tell you that you'd have zeros at 3 and negative 1. But it also has vertical asymptotes at 1 and negative 1. But what happens is, since this one simplifies out, even though those go away, the asymptote is still there, but because it becomes a 0. You get these weird problems that you can get a hole in something that still occurs. I know, and that's the idea. I don't want to, you see a lot more of this next year. It's just, what I just want to get you guys accustomed to, really for Algebra 2 purposes, is can you identify asymptotes? Can you find zeros? Can you find your vertical asymptotes? And then really the next step that I'll have you guys do are those slants. That's kind of the bigger push that I'm going to get you guys through. Next year, you guys will talk a whole bunch about this discontinuity thing and about limits of what's happening there. What's the one?
How do you find the slant asymptote for number
19. What was? Oh, I guess I could just do this. Are we okay on that one then?
19? Yeah.
All right.
19 is y equals x.
Okay. When you get these, oops, there we go.
If the n is bigger than n.
What happens here is that, oops. Obviously, for this case here, when you do this, you've got your zeros in the numerator. It's just 3. Okay. If you, we talked about this yesterday. There's no reason to factor out a difference in cubes for this stuff. We talked about that, right?
Yeah.
Because the quadratic is generally imaginary, so you don't. I mean, you can think about it.
Took me a while.
Why do you guys? I'm trying to be nice. And then, yeah, it's at 3, and then the vertical asymptote's at 0. The degree is bigger than the bottom, so there's no horizontal. So if you start thinking about what this would look like, we have the 0 and x-intercept at 3. All right. Well, that means there's a lot of numbers I don't know what's going on here. So I'm gonna check. I would check it at 1 and 2 and whatnot. But for time purposes, I'm going to say that I'm doing all of that extra work. Don't judge. Don't judge. What's that? Now, one of the things that's going to happen when we start looking at graphs like this, if you put this in your graphing calculator, you notice that you see a little hook and then a long line going through. If you start messing around with your window, if you make your your y maximums and minimums like a plus minus 100, let's see if this hooks it. What's happening is this won't have that traditional slant to it. And the reason is because the degree of the numerator is 2 more than the denominator. Okay? We'll get the slant asymptote when it's 1 degree more. Yeah. Yeah. No, because there isn't technically a. Yeah, but if you look at it, if you split it out this way, what I did is I split it for plus minus 100 for my y values. Your slant would be, I mean, you can say they would be approaching the same thing.
Yeah.
So here, if it was 1x, I mean, if I threw 1x there, this tail isn't approaching that. This one's going the other direction, you know. But if this was if it was x squared minus 27, I bet you could probably make that work. We just change that. Yeah. See, if you do it this way, if you do it with the x squared, you've got this slant going here. All right. And that's where it comes into play. And we'll do a lot of those tomorrow. It's exciting. Can you please have like a little bit of faith in me? Thank you. Appreciate it. Makes me feel better about everything. What's wrong with my tie? No.
Connor?
This is blue and like brown.
That's yellow. That's yellow.
There's nothing wrong with this. There's brown and blue in my shirt. There's brown in my shirt. Did we do? Did we do? We didn't do this one yet, did we? No. I'm gonna do.
Mr. Murphy,
Yes, ma'am.
look at this.
Let's grab this one.
I showed my cousin and he started crying. He was laughing so hard.
What?
I was gonna ask what you would write for the vertical asymptote if it's like on number 17, it's 3x squared minus 9. And so if you set that up to 0, then like you get stuck halfway through. So
I know. If you move, you divide, you subtract 9, divide by 3, you'll get plus minus root 3. So your vertical asymptotes are plus minus root 3. That's it.
Okay.
That's all. And then you fudge it on the graph. But your asymptotes can be asymptotes can be roots. That's fine. Okay. So I want to walk you through another one real quick, and I'm going to add a couple problems to this for you guys. I want to walk you through that scenario when you get the multiple selections on where to choose values to graph. Okay. I want to graph this one fully. I'm going to do all of the asymptotes. I'm going to find all of the breaks, and then I'm also going to plug and chug and figure out some values that make it work. Yes, you guys have respect. Like these bozos. Don't hang out like that. Alright, so in this one here, this is a pretty quick one to go through. You wind up with an x-intercept at 0. We okay with that? So we have y equals 3x squared over x squared minus 4. I have an x-intercept at 0 because I set the numerator equal to 0. You need a couple push-ups, you couldn't throw the ball that far. I have vertical asymptotes. Look it over. It'll be at x equals plus or minus 2. We okay with that?
Yeah.
All right, all I did was just set equals 0 and solve for x. Now I go to the horizontal asymptotes, and I have to think about the 3 cases. 3 cases here, I have the degrees are the same. The 3 cases, the degrees are the same, which means it's the coefficients, just like it was back on Tuesday. So the horizontal asymptote is going to be at y equals 3. From that, we now have plenty of information to rough sketch the graphs. And again, just like you were asking earlier, what happens when you've got those 3 different domain areas? You're just going to pick values within those 3 domains and plug and chug. Okay. So if I go to graph this, start with your x-intercept, 0. Vertical asymptotes at plus minus 2. and horizontal at, what was it, 3?
Yeah.
At 3. Oops. And again, like we said earlier, you'll notice that you've got 3 sections of domain to worry about. So when we did this back on Tuesday, remember I always said pick a couple on either side of your vertical asymptotes? Do the same thing. So if I have a vertical asymptote at -2, I'm going to try, I don't know, -3, -5. That way I can see what's happening as it's going further away. And then I'll check them at -1 and +1, it's between. And then I'll do the same thing on the other side, 3 and 5. Unlike the problem before, this one, when you do your -3 and +3, you're going to get the exact same answer because there's no x term. You're just squaring it, and it's going to work out. So it seems like there's a lot more there, but you're going to get the same y value for both of them. Okay? So you go through it. What's -3 squared? 9 times 3 is?
27.
27. So the numerator for the first one will be 27. The denominator will be 9 minus 4, which is 5. So this is 5 and 2/5. So at -3, we are at 5 and change. And now I do it again with -5. Oh, but remember, it's the same thing here, so it'll be at 5 and 2/5 here as well. What's wrong? Why? Why did I skip 4? Oh, I didn't put it at 5, I put it at 3. No, the reason why I skipped 4 is because I know that's up in those, now I know it's up in those further out quadrants. If I pick a number further away, I can tell, I might have a better idea of how fast it's curving away or inward just by picking the next number outward. That's all. You can choose 4. I'm just guessing that if I have a little bit more space to it, I might get a better idea. That's it.
Are you sure it's So if there's not 2 vertical asymptotes, you just do like one side and the other side? Okay,
Yes,
so
and then you start thinking about, okay, is this enough information, or do I have to pick up a tailor out here or there?
So like let's say the vertical one on the right isn't there, you'd only have to do like -3, -5.
Yeah, you might want to bounce around just to see what happens. And then just maybe pick like a -10 just to see if something else did occur, just to get a guess. -5, so you get 25. 25 times 3 is 75. 25 minus 4 is 21. That is what? Goes in 3 and something? So it's 3-ish. 3 and 14, 21st. 3 and 2, yeah, it's 3 and 3-ish. So at 5, we're at 3-ish. 5 and 3-ish. So now you see how it's lower than the first set of ordered pairs? So that tells me that there's a curve, and it's bouncing between the 2 asymptotes. Okay? And I do the same thing with 1s. So I get 3 over -3. I get -1. And -1. Would it be wise to just double check to see if it doesn't go any higher by just using a 0.5 real quick? It wouldn't hurt. You know, it wouldn't hurt just to use a 0.5 real fast, just to see if something funky didn't happen. You know, because it looks like it's going up and coming back down. So if we check and see if you use 0.5, if it's between 0 and 1, 0 and -1, you should be all right. So let's see here, 3 times 0.5 squared, divide that by 0.5 squared minus 4. I get -0.2. Okay, so we're okay. So that's basically telling me that this graph does this. And you get some really funky domains and ranges then.
How would you list those?
I'll show you. You write it between the three different sections. You go through your domains. So your first domain, if I'm looking at the domains here, well, my domain values of x that are less than -2, my range values are above y values that are greater than 3. See what I'm doing there? And then the next one, when my domain is greater than -2, but smaller than +2, my range is all values that are smaller than y values that are smaller than 0. But did it equal 0?
Yeah.
So all my range values are smaller than that. And then I do the same thing for my last domain. So you have x values that are greater than 2, and the range, or the y values are greater than 3. And you get these multiple domain range styles for this type of problem. I honestly don't think the book ever asks you to list out all the specific domain ranges, but I do know that you will do that via set notation next year in pre-calc. So if you understand the idea of, you're just looking at what's happening between each of those sections. Yeah, that's it. That's really it. And you'll write it a little bit differently than this, but other than that, it's the same basic principle. Okay? It's a good question. It's a messy problem. I love them. Great.
It's really easy to list though than the other ones.
Yeah. Yeah, the first few that you guys were listing out stuff, those problems were made for have you guys just find your asymptotes really, because if you start trying to plot and graph, those are awful. That's why it just says list them.
You drew stingrays and a polar bear. Yeah, there's stingrays and a polar bear. Okay, like look at
Yeah. Just out of nowhere, Hopwar's like, yeah, okay. How is that a polar bear?
It has 2 eyes and a nose.
The bottom one looks like an
Like you're looking down at
Yeah, it's
it.
got a nose and 2 eyeballs.
Like you're looking from like the sky and just like polar bear.
Because it's on white paper, so it's a polar bear. If you're a white bear, then you're gonna hide, because all the animals are gonna see you. Okay, but
why
it looks like a
mouth,
polar
why
bear
nose
looking
and 2
up.
eyes. We're assuming this is
Got
a
a
bear.
nose and 2 eyes.
Anywhere.
I mean, go ahead. There will be.
Why do we assume by
She's like, kiss herself when it's on
Yeah,
camera.
right? Yeah, like the actually
I was
surprised.
But no, you have to like. I would not see there's an arm and there's another arm. Oh, I see it now. Yeah.
I know. Okay, all I'm saying is you can't assume that's a polar bear.
And then is there a baby seal out here?
That was
Trying to
the
chase?
That's the stingray has that's already the band's great. And it looks more like that. The stingray
All right. Wow. Hey, I want you guys to do. Yeah. If I'm not mistaken, I know in second hour they had basically spots for 3 more graphs. I want you to walk through numbers. Oh, why is this taking?
It's a stingray. It will sting you and you'll die.
Okay, Jada.
If it stings you on your heart, you'll die. Don't say that.
There it goes. What's that? I think I posted these 3 here. I'm not sure. I want you to do 30, 31, and 36. All parts. All part.
Is it connected to the other one?
Yeah, and then let's turn this in tomorrow.
So all three assignments of the summer together?
I'm gonna do it on a different graph.
Yeah, Levant.
Do we have to find domain and range?
Yes, please. Yeah, with all parts. What I mean by that, also domain and range. Also, okay. So think of it this way: you want to do your x-intercepts, vertical asymptotes, horizontal asymptotes. I want you to graph it, which means list some ordered pairs within all those. Just 30, 31, and 36. Those three of them. Because I know that this can take a little bit of time to go through them. So that's why I just was going to give you three of them. Yes, ma'am. It's the same page that it was last night. I forgot. Was it 550? Yeah, it's the exact same page. It's just three more problems. Yeah, go right ahead. Yeah, if you want to take a picture, then we don't have to open anything up. Which ones? It's 2x squared, 3x, and 1. Izzy! What's up? How are you? I'm good. Good to see you. Look, we're doing rational graphing. Don't you remember how much fun this was? So do they, but they don't get to use it.
Sadly.
Where you at? Calc 3 now? Nerd.
I got a friend for
You did? Nice work. That's great.
It's okay. I got it. Okay. Izzy! Oh my god, that's my little sister.
No way.
Related to her sister.
No, I didn't know that.
And that's Val's little sister. Can you see me and Val and our little sisters?
See you. Good to see you. Calc 3. What a nerd.
That's the math teacher.
Right. No, Izzy's a good kid. She worked really hard. She did really well.